अभी फार्मिंग और है और जियोलॉजी एंड माइंस डिपार्टमेंट में है। तो अभी
मैं एक्चुअली क्यों पूछ रहा हूँ, मैं एक प्रोजेक्ट कर रहा हूँ ड्यू ड्यू वाटर हार्वेस्टिंग का। ड्यू को तुम लोग क्या कहते हो गुजराती में? जाखड़, झाखड़।
हाँ 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 जाकर।
तो ड्यू वाटर हार्वेस्टिंग का एक प्रोजेक्ट कर रहा हूँ। उसमें गुजरात के डिफरेंट लोकेशंस पे मैं अपना हार्वेस्टर लगाता हूँ और उसमें कितना ड्यू फॉर्म होता है उसका मेजरमेंट लेता हूँ ऑन डेली बेसिस।
ओके।
This harvester is a passive harvester. There is no electronics there. It is just a surface that that promotes, not promotes, that supports dew. So productivity of that surface is quite good. तो लास्ट ईयर जो मैंने रीडिंग लिए थे पोरबंदर में, मैं किसी एक साहब को जानता था, उनके घर पे मैंने पोरबंदर इज वन ऑफ द लोकेशन फॉर, उनके यहाँ मैंने लगाया था। बट अनफॉर्चुनेटली इन वेव 2 he passed away. Now I don't have any location in or around Porbandar where I can set up my harvester. Therefore, I am asking if you can help me. तुम पोरबंदर शहर से कितने दूर रहते हो?
अराउंड सर 35 किलोमीटर।
टुवर्ड्स द्वारका और
हाँ
टुवर्ड्स
हाँ,
सोमनाथ?
द्वारका, यस द्वारका। मतलब मेरे घर के पास द्वारका और पोरबंदर का मतलब जो बॉर्डर होता है ना वहाँ पे ही एकदम।
तो मैं अगर हार्वेस्टर तुम्हारे घर पे पहुंचाऊं या भिजवा दूं तो ये काम ऑलरेडी 2-3 महीना लेट हो गया है। अक्टूबर से ड्यू फॉर्मेशन स्टार्ट हो जाता है। इट इज ऑलरेडी एंड ऑफ फेब, बट स्टिल वी हैव 1.5, सो करीब 30-45 डेज अभी बचा हुआ है। सो वुड यू और एनीबडी फ्रॉम योर हाउस लाइक टू हेल्प मी?
अभी तो
नहीं,
सर
क्यों इतना सोच क्यों रहे हो? इसमें पैसे मैं नहीं लगा रहा हूँ, पैसे तुम्हारे नहीं लगेंगे। तुम घर पे रहते हो ना,
हाँ यस सर।
तो इसमें सोच क्या रहे हो इतना? आई थॉट दैट आंसर इज स्ट्रेट यस। So what is coming in your mind which compels you to think?
मतलब सर इसके प्रोसेस क्या होगी अगर
कुछ
आप
नहीं,
भिजवा।
कुछ नहीं। एक स्ट्रक्चर 1 मीटर स्क्वायर या 1 मीटर क्यूब का एक स्ट्रक्चर आपके खेत में या आपके घर के सामने कहीं रखा रहेगा। केवल सवेरे आपको उसकी रीडिंग लेनी होगी, उसमें जितना ड्यू फॉर्म होता है। एक बॉटल में ड्यू कलेक्ट होता है, उस
ओके।
बॉटल से ड्यू निकाल के उसका मेजरमेंट लेना है कि कितना ml ड्यू हुआ, और उसको एक बड़े बॉटल में स्टोर करते जाना है। दैट इज ऑल।
हाँ तो सर ठीक है मैं तो कर दूंगा।
नहीं, बट फर्स्ट टेल मी व्हाट मेड यू थिंक सो लॉन्ग? व्हाट
नहीं सर मैं सोच रहा था कि इसकी मतलब प्रोसेस क्या होगी और क्या क्या करना होगा तो।
and that you did not want to bother yourself?
नहीं सर ऐसा।
अगर मान लो कुछ करना भी पड़ता, सपोज थोड़ी 10 मिनट आधा घंटा कुछ मेहनत भी करनी पड़ती,
हाँ तो सर उसमें कोई प्रॉब्लम नहीं है वो तो।
नहीं, बट नाउ आई एम हेजिटेटिंग इन आस्किंग यू फॉर हेल्प। क्योंकि अगर तुम सोचने लगे इसका मतलब है कि यू आर नॉट वॉलंटियर। एनीवे, सो लेट अस स्टॉप दिस डिस्कशन। But slightly I felt bad. कोई काम इसमें नहीं। खुशी साने पड़ा। खुशी,
यस सर।
अभी मैंने किसका नाम लिया था? यूएई वाली लड़की। हैज शी कम टू द क्लास? व्हाट वाज हर नेम? नहीं नहीं, अभी मैं किसी का जो यूएई की है।
यस सर।
आशका।
यस सर।
आशका, यू आर आशका?
यस सर। गुड मॉर्निंग सर।
हाँ, तुमने जो मोबाइल नंबर भेजा था ना, उससे मैं कंफ्यूज कर गया था कि
ओह।
तुम्हारा कंट्री कोड है 971
यस।
951
नो
971।
971 सर।
मुझको लगा कि 7 यू हैव रिटन, मतलब इट वाज अ टाइपो बिकॉज इंडिया
ओह।
कोड इज 91।
यस सर, +91 या।
मैं कंफ्यूज कर गया कि शायद तुमने गलती कर दी। मैंने सारे डिजिट काउंट किए तो वो थोड़ा ज़्यादा हो रहे थे। मैंने फिर तुमको नहीं कॉल किया। फिर मैंने नेक्स्ट वाज किशन। फिर किशन का नंबर मुझको मिला तो किशन को मैंने कॉल किया। ऐसे भी तुमको कॉल करता तो मैं तो शायद कर नहीं पाता, क्योंकि इट इज इंटरनेशनल। इज इट कंसीडर्ड टू बी इंटरनेशनल कॉल और लोकल कॉल? दुबई के लिए क्या होता है?
So it's considered as an international call, and actually, one more thing is that many of the video calling and voice call apps are banned over here, like WhatsApp call and all. It doesn't work here. Even
क्यों?
Google Meet. So I don't know it. There was issue because of which they banned all these apps. Even Google Meet never used to work, but since the pandemic came and schools over here had to teach online, so they enabled Google Meet. Otherwise, even that was blocked.
ओ वेरी स्ट्रेंज।
Yes, sir.
जूम जूम है या नहीं?
Yes, so they even enabled Zoom now because of the pandemic. Because some schools teach through Zoom and some teach through Microsoft Teams and some even use Google Meets. And like these three platforms have been enabled. Otherwise, the other platforms they just don't work. Like missed call, maybe you will get a missed call, but you'll not be able to hear the other person.
अच्छा, so I thought that Dubai or UAE is a different kind of country, not a typical Muslim country.
Actually, there was some issue that happened because of which they blocked all these apps. That's why.
No, so the basic logic is like they want to promote the local players. There are like two providers like Etisalat and Do. So they want to promote their plans. So बाकी सब फिर FaceTime फिर ब्लॉक कर दिया है वैसा है और WhatsApp कॉल भी ब्लॉक कर दिया है।
हाँ, बट उससे कोई फायदा नहीं हुआ ना, क्योंकि प्रमोट तो हुआ नहीं। इंटरनली प्रमोट हो सकता है।
People are buying। हाँ, पर VPN लगा के फिर यूज कर लेते हैं।
तो VPN किसको लगाना होगा, मुझको या UAE वाले?
नहीं, हमें ही। अगर if you want to use WhatsApp call and FaceTime then VPN यूज करना पड़ेगा। But there is a huge fine on that, but usually लगता नहीं है।
हमें मतलब UAE वाले को या इंडिया वाले?
या सॉरी, या UAE वालों को। हाँ,
तो तुम भी UAE में हो?
यस सर।
अच्छा, यू आर ऑल्सो।
मैंने सर हाई स्कूल वहां से की है, 9 to 12।
अभी कहाँ? अभी कहाँ
अभी
हो?
इंडिया हूँ सर, अहमदाबाद।
So your admission is as Indian national admission or NRI?
नो सर, फॉरेन नेशनल।
So your parents are in Dubai.
नो सर, दे आल्सो हैव शिफ्टेड विथ मी।
They shifted with you or you shifted with them?
आई शिफ्टेड विद देम।
एडमिशन के बाद या एडमिशन के पहले?
हाँ सर, एडमिशन के बाद।
शिफ्ट करते तब तो नहीं होता है। ओके, विशुल विशुल प्रजापति। विशुल प्रजापति नहीं, क्या है? नहीं, बुशिल भवसार। विशुल प्रजापति कौन?
Yes, sir. Good morning, sir.
तुम्हारा नाम क्या है? बुशिल भवसार।
Yes,
बुशिल।
sir.
तुम कहाँ
मुश्किल
रहते हो?
हिम्मतनगर सर, साबरकांठा।
तो तुमने मोबाइल से क्यों ज्वाइन किया हुआ?
सर ये लैपटॉप में अपडेट हुआ ना, तो पता नहीं कुछ स्ट्रेंज बिहेव कर रहा है लैपटॉप, इसलिए आज मोबाइल से ज्वाइन।
अच्छा, बाकी लोग अपने को म्यूट पे रखें। कल एक लड़के को मैंने बहुत डांटा है इस कारण। बैकग्राउंड से किसी और के इससे आवाज़ नहीं आनी चाहिए। अभी कोई आवाज़ आ रही थी। चलो ठीक है, मैं शुड आई स्टार्ट नाउ? इट इज़ 10:26। आई शुड। Right. So the last class we discussed this graph in detail, and this graph is particularly for group 4 element. Group 4 element means in the outermost cell, that is n is equal to 3, there are 4 electrons, and we discussed what would happen if there are n such atoms which are brought very close to each other. So the number density of such atoms or such material or such crystal is typically around 10 to the power 15 per centimeter cube to 10 to the power 19 per centimeter cube. So in 1 centimeter cube volume, there are 10 to the power 15, 10 to the power 13, 10 to the power 17, 10 to the power 19, depending upon in what form we want to use that material are there. So it is a huge number. It is a huge number. And therefore, in the outermost cell, that is n is equal to 3, there are 4 into 10 to the power 15 electrons. Since no two electrons occupy same energy level, therefore the energy levels split. So energy level of 3s and 3p of each atom is split, and that makes band. So at certain stage of interatomic spacing, that band is sp hybridized band, and which is if there is no facility for marker or laser pointer. So that band is here, where there is no discrimination or no identification of s or p orbital. When interatomic space increases further, decreases further, then those 8n states split further and gets divided into two separate bands, and those are one which is lying up and one that is lying low. The lower band is called valence band, the upper band is called conduction band. The definition of valence band is that all outermost orbit electrons lie in valence band, and therefore there is no space to move around for those electrons, and so they are behaving as an insulator at absolute zero temperature. And the property of this conduction band is that there is empty space and no electrons, no free electrons to move. So the moment, by virtue of some mechanism, the moment I make one electron jump to conduction band from valence band, so this transition, if this transition happens, then that electron which is now in the conduction band, it finds itself free to move anywhere in that conduction band, that surface of conduction band, or in that volume of conduction band. Since electrons are free to move in conduction band, therefore we call that the material starts conducting. So if you are asked that why a silicon atom at absolute zero is a typical or is a very good insulator, but after or raising the temperature or at room temperature it conducts slightly, and by means of some other mechanism it actually conducts very well. So you should know the reason, or you should be in a position to explain the reason, your answer. The last class we also touched upon that why it is necessary to see a bigger atom or a system of atoms or a crystal or a molecule, whatever you say, in form of, in model sense of modeling, form of closest to a hydrogen atom, so we call it hydrogen like atom. So what happens in modeling any atom as hydrogen like atom, what we actually see is that in that case we take the typical core. So core comprises of nucleus and other than the outermost orbital electrons. In case of silicon, if n is equal to 3 is the outermost orbit, then up to n is equal to 2, all electrons are considered in the core atom. So 2 electrons of n is equal to 1 and 8 electrons of n is equal to 2. So 10 electrons and the nucleus, all these make the core, and the 4 electrons of outermost orbit will be considered as negative charge, 4 negative charge revolving around a core of 4 positive charge continuously. At that beam, Z is equal to 11. So it is perhaps sodium. In that case, in the outermost orbit, there is only one electron. And in that sense, the hydrogen-like configuration fits perfectly well. That a core, an electron of charge -1 is revolving around a core of charge +1, which is hydrogen atom. So if you have to study sodium atom, hydrogen-like configuration fits pretty well. But in other cases also, we are closer to hydrogen-like atom in some sense, and therefore the study or modeling of theoretical modeling of such atoms is done in that form. For the next element in group 4, which is germanium, Z is equal to 32, can also be depicted in the same form, that there is a core and there is outermost orbit, but in this case the outermost orbit is n is equal to 4. So the 4 negatively charged electrons are always negatively charged, so 4 electrons are revolving around the core atom of Z is equal to 32, which has 28 electrons in its core. So plus 4, 28 electrons and 32 protons in nucleus. So plus 4 in the core. Core atom is plus 4 charged, and the outermost orbit electrons are minus 4. So eventually it is a neutral atom, but we model it like that. We model it like that. So the difference between a isolated silicon atom and an isolated germanium atom is that only that in this case, in silicon's case, the core has 10 electrons, and in case of germanium, core has 28 electrons. So these 28 electrons will repel the outermost 4 electrons strongly than the core atom of silicon, which has only 10 electrons. So 10 negative charge will repel 4 negative charge feebly in comparison to 28 electrons of core in case of germanium repelling 4 electrons in the outermost orbit more strongly. So that is the only difference in electrostatic discussion of germanium or silicon, and therefore overall energy configuration of silicon is different from overall energy configuration of germanium. On that basis, so you know what is crystal, you know what is a unit cell, you know what is length of unit cell. So if a crystal is considered to be as a cube, then the side of the cube is basically called A, or the length of the unit cell. So now consider that there is a crystal of silicon, there is a crystal of germanium. Can somebody tell whose A, or the length of unit cell, is more and whose A is less? Can somebody tell me? Case of silicon and germanium, these two are of the same group, group 4. This slide I have written that A is equal to 5.43 angstrom in case of silicon. So do you think that A of germanium is more than 5.43 or less than that? Who is taking this question?
It will be more, sir, because the electrons are the outer inner part are more, so they are repelling the outermost cell. So I think it will be more.
So sorry, because what did you say?
You said the number of electrons in the inner parts are more, so outermost cell will be repel more. So that's why.
So it is not because I said it is. Germanium is a bigger atom than silicon. So if you are keeping such atoms in form of a crystal, then also along that side of the cube, there are two bigger atoms. So their interatomic separation or their internuclear separation will be certainly bigger. So if you ask two fat persons standing side by side, then the difference between the navels of those two fat persons will be more than if you ask two thin persons stand side by side, right? So that navel you may consider as nucleus. So since internuclear distance between two fat persons is more, even then there are two persons only. Similarly here, since germanium is a fatter electron atom, therefore the interatomic or the A of germanium crystal is more than the A of silicon. Okay, so silicon and germanium has a very unique crystal structure, and the name of that, because of that uniqueness in crystal structure, that crystal structure is given a special name, and that is zinc blende. Diamond is also similar type of crystal structure, but diamond is said diamond structure. So diamond structure crystal and zinc blende structure, these are two different type of crystal structures. Okay, so silicon and germanium, if I ask you what is the crystal structure name of silicon or germanium, the answer should be zinc blende.
Sir,
Bolo.
sir, why is it structure is named zinc blend for silicon and germanium?
अब ये तो मैं नहीं बता सकता हूँ, जो नाम रखा तो रखा. I don't have answer to that. Zinc blend, इसने नाम रखा होगा, उसको क्या, I don't know. Tell me another thing. How do we calculate atoms per unit cell in a crystal? So there are various types of crystals. Simplest is simple cubic, SC. The next one is body centered, BCC. The next one is face centered, FCC. The next one is HCP. HCP is how it is abbreviated. So there is HCP. So there are various structures of crystals depending upon how many atoms per unit cell are there. So how do we calculate that per unit atoms per unit cell? So if you consider one cube, it has 8 corners, right, and 6 faces, right? So each cube can share its walls or faces with 6 नहीं, एक क्यूब बनाओ. So there are 6 faces, so one cube can share its sides with 6 different cubes. So each center occupying atom is shared at each center, at each corner. There are 8 cubes which are meeting. So each atom is shared by, so for one cube, 1/8 atom is considered to be the part of that cube, and there are such 8 corners. So in the simple cubic structure of crystal, we say that it has 1 atom per unit cell. Instead of simple cubic, if we have body centered, BCC, and because of 8 atoms on its corners, there is 1 atom per unit cell, which we just calculated, and one sphere or one atom is in the center of the cube, which is not shared with any other cube. So in BCC, there are 1 plus 1, so 2 atoms per unit cell. If we consider face centered, FCC, so there are 6 faces, and each face is shared with another cube, adjacent cube. So each face centered sphere or atom is shared between 2 cubes. So half per unit cell contribution comes from there. There are 6 such faces. So half into 6, 3. 3 atoms per unit cell comes from face centered atoms, and 1 atom per unit cell comes from corner sitting atoms. So 3 plus 1, 4 atoms per unit cell is the atom per unit cell calculation for FCC. So similarly, in case of zinc blend structure, it is written again on this slide that there are 8 atoms per unit cell. A zinc blend structure, I am not showing it to you in this today's class because I want you to study also. So you browse it, you Google search it, you read it in any textbook, any semiconductor physics book. What is zinc blend structure? The zinc blend, I just define it. Zinc blend structure. So you take one simple cubic structure, and then what do? You draw the diagonals, body diagonals. So there are 4 body diagonals in any cube, right? On each body diagonal, 1/4, at 1/4 distance from one corner. At 1/4 distance from one corner, there is one atom sitting inside the cube. Because the valency of silicon is 4. Outermost orbit has 4 electrons, so it will tend to bond with 4 neighboring atoms. Okay. To make it 4 plus 4, 8 electrons to make it a stable structure. One corner is actually connected with 3 atoms. Three other corner sitting atoms. So there is one valency, there is one vacancy for that atom to connect with. That one connection may come from the neighboring cell, neighboring cube, or it may come from this 1/4 distance lying atom which is inside the cube. And therefore it is alternate. Not all corners have 1/4 distance lying atom inside the body or inside the cube. Otherwise 8 हो जाते अंदर में, लेकिन नहीं. After each, so if you start from top left corner, then you skip the top right atom corner. Then you move again anti-clockwise, then top upper right, not. If you start from top surface, left corner, move clockwise, you come to the right of top, then you move clockwise, you go to the back right, not front right, back right, rear right of that top surface. So from that corner, again 1/4 body diagonal, there is one atom sitting inside the cube. Then you move to the 4th corner of that surface. You have to skip that. You come down, draw the body diagonal, which is the front top corner. On that body diagonal, 1/4 from that atom. That atom means the back bottom corner, back side bottom corner. So back side bottom corner has 1/4 distance lying atom. Then you again move anti-clockwise. You come to the bottom surface, front left corner. So उस तरीके से जब आप move करेंगे, skipping one consecutively, then you find that each 4 of the corner atoms are attached with one atom each, lying on the 1/4 distance on its body diagonal. तो बचे हुए 4 कॉर्नर एटम होंगे वो अपने नेबरिंग सेल के नेबरिंग क्यूब के एटम से कनेक्ट होंगे। तो इस तरीके से वो 4। So these are the 4 atoms which are lying inside the cube, which are not shared by any other. Which are not shared by any other cube. And therefore, zinc blend structure has 8 atoms per unit cell, and the atomic length or the length of the unit cell is 5.43 angstrom. जर्मेनियम के केस में इससे slightly bigger होता है. So now tell me, and the density, number density is 5 into 10 power 22 atoms per centimeter cube. Now tell me, if I replace, so in case of silicon metal, all atoms are silicon atom. In case of germanium atoms, all atoms are germanium atoms. But you have known, or you have informed that there is another semiconductor material which is very highly used, and that is called gallium arsenide. And gallium arsenide, as I told you, is a 3-5 material. So gallium के outermost orbit में 3 इलेक्ट्रॉन हैं और आर्सेनिक के outermost orbit में 5 इलेक्ट्रॉन हैं. ये दोनों combine होके they create 8 electron structure, and therefore they make a stable structure. In the same structure, similar to silicon's zinc blend structure, can you visualize how gallium arsenide crystal is formed? Can you visualize how gallium arsenide crystal is formed? Who will take this question?
Sir, in gallium arsenide, the sum of gallium atom will be replaced by arsenium.
Arsenic.
Arsenium, yes sir.
नहीं, बट गैलियम कहाँ रहेगा और आर्सेनिक कहाँ रहेगा? गैलियम का कोई क्रिस्टल, जैसे सिलिकॉन बना रहा है वैसे गैलियम, प्योर गैलियम का क्रिस्टल हम नहीं बना सकते हैं, बिकॉज इट हैज 3 वैलेंसी. तो 3 वैलेंसी का हम क्रिस्टल बनाएंगे तो इट विल ऑलवेज शॉर्ट ऑफ 2 इलेक्ट्रॉन्स. 3 है ना, तो गैलियम के साथ ही अगर वो कंबाइन होगा तो 3 3 6 हुआ, तो 2 इलेक्ट्रॉन्स अभी भी उसको शॉर्ट रहेगा फॉर मेकिंग अ स्टेबल स्ट्रक्चर. सो इट इज नॉट स्टेबल. So gallium will always make a stable structure with group 5, that is sure. That group 5 is arsenic. Again, that is, so who is gallium's friend is known. But अभी मैंने सिलिकॉन के केस में बताया कि सिलिकॉन के केस में क्यूब के 8 कॉर्नर पे एक सिलिकॉन एटम है, और सिलिकॉन के बॉडी के अंदर 4 और सिलिकॉन एटम है, lying alternatively on body diagonals. जो 4 बॉडी डायगोनल है, उन चारों बॉडी डायगोनल पे वो 1/4 डिस्टेंस पे एक एटम बैठा हुआ है, एक ऊपर से एक नीचे की तरफ, अल्टरनेट बॉडी डायगोनल. और इस तरीके से सिलिकॉन का क्रिस्टल बना. गैलियम आर्सेनाइड में which place will taken by gallium, which place is taken by arsenic, or they have some different structure? They should have some different structure.
सर सर ये इस सिलिकॉन के स्ट्रक्चर में हम एक सिलिकॉन पेयर कंसीडर करें, 2 सिलिकॉन एटम जो एडजेसेंट है और कनेक्टेड है बॉन्ड से, तो उसकी जगह पे हम गैलियम और आर्सेनाइड का पेयर रख सकते हैं, क्योंकि 2 सिलिकॉन में टोटल होंगे 8 इलेक्ट्रॉन और उसमें से एक बॉन्ड बना हुआ है, तो टोटल 6 इलेक्ट्रॉन है, तो वो 6 बॉन्ड बना सकता है. और गैलियम आर्सेनाइड में भी 3 और 5 मीन्स टोटल 8 इलेक्ट्रॉन है और एक इलेक्ट्रॉन पेयर बॉन्ड में यूज हुआ है, तो उसमें भी 6 इलेक्ट्रॉन है, तो वो भी 6 बॉन्ड बना सकता है।
तो तुम कह रहे हो कि क्यूब के जो 8 कॉर्नर हैं उनमें अल्टरनेटिवली एक में गैलियम एक में आर्सेनिक हम डालेंगे।
यस सर।
एंड देन विद इन द बॉडी जो 4 और साइट है ना एटम के, गैलियम आर्सेनाइड के क्रिस्टल का जो यूनिट सेल है इसमें 4 एटम विद इन द यूनिट सेल हैं जो बॉडी डायगोनल पे हैं 1/4 डिस्टेंस पे। उसमें कौन रहेगा फिर?
हेलो सर।
हम्म
आई थिंक सर बॉडी डायगोनल पे गैलियम आएगा और बाकी के प्लेसेस पर आर्सेनिक आएगा, कॉर्नर एंड साइड पर।
सो 8 कॉर्नर पे आर्सेनिक आएगा
आर्सेनिक,
और बॉडी के अंदर जो 4 हैं उसमें
हाँ गैलियम आएगा, वो कंप्लीटली
गैलियम
4 आते हैं ना।
और अल्टरनेटिवली और अदर वे ऑल्सो चारों बॉडी 8 कॉर्नर पे गैलियम आएगा और बॉडी के अंदर आर्सेनिक आएगा।
यस सर।
हाँ यस सर, ऐसा ही आएगा।
ऐसा ही आएगा। ठीक है। So I suggest you all to see the crystal structure of silicon and gallium arsenide separately and carefully. I may ask you to draw it. While drawing it, since you are doing it with either pencil or pen, you might not have different colors with you. So while drawing it, you have to differentiate between gallium and arsenic atoms in your drawing. तो एक को डार्क कर सकते हो, एक को ब्लैंक रख सकते हो और उसमें तुमको दिखाना पड़ेगा कि डार्कर इज गैलियम एंड ब्लैंक इज आर्सेनिक और वॉट एवर यू वॉन्ट टू शो, बट you have to be very very particular and careful while drawing these crystal structure to convey what you want to draw or how these crystals are formed. ठीक है। गैलियम आर्सेनाइड के क्रिस्टल का नाम है डायमंड स्ट्रक्चर और सिलिकॉन एंड जर्मेनियम के क्रिस्टल स्ट्रक्चर का नाम है जिंक ब्लेंड स्ट्रक्चर. So I may also ask you, instead of giving the name that draw silicon crystal or draw gallium arsenide crystal, I may ask you draw a zinc blende structure. In case of zinc blende structure, there are no two types of atoms. There is only single type of atom. Either you can make them dark or you can make them blank. So just line, a circle drawn by a line. But if I ask you to draw a diamond structure crystal, then you have to differentiate between different types of atoms, and there is marks in that. Okay, so हमने कल I told you that in next class we will try to see the bond model of lattice. So this is one 3-dimensional, or rather in this picture it is 2-dimensional. So this is one 2-dimensional array of some such crystal. 3-dimensional ये तब होगा जब इसके टॉप पे और नीचे, so z axis के along. If your screen of laptop is xy axis, then along the z axis, if we keep adding such type of array of atoms, then it is a 3-dimensional structure. And this is group 4, silicon. So you can see that there are 8 lines coming out of each circle. 4 lines belong to that atom and 4 lines belong to the neighboring atoms. Each line represents 1 electron. Each line represents 1 electron. So, if this is the outermost orbit electron of this atom, then this is outermost orbit electron of this atom. This atom is combined with this atom by this line. So, this electron. So, these two electrons of one each atom are shared. Similarly, if this line is 1 electron of this atom, silicon atom, outermost orbit, valence electron, then this line belongs to this atom, valence electron. So, these two lines, by these two lines, there is a bonding between this silicon atom and this silicon atom. Similarly, these two lines keep this atom and neighboring atom which is sitting here bound together. Similarly, these two lines keep this atom and the neighboring right side atom bound together. So, one center silicon atom is bound with these 4 neighboring atoms by virtue of this type of bond structure, and that is how this crystal is created. This is the bond model. Now, this is what I want you to focus on, which is what will happen since I said you that each line represents 1 electron. What would happen if 1 electron by some means, right now do not bother how, but by some means 1 atom escapes. So, if this 1 atom is shared between these two atoms, there certainly is one bonding energy by which that atom is shared between these two atoms. If I supply more than that bonding energy to these two atoms or to that bond length, that electron can escape. That we know from our high school knowledge. So, escaping 1 electron from such type of array of bonding or array of atoms is quite simple. Just you have to add some energy. Just you have to give some external energy to that crystal. One means of giving external energy to the crystal is heating it up. Another way of giving external energy to the crystal is by shining light on that. Okay, so 1 electron can escape. Then what would happen? If this electron is escaped by adding some external energy to the crystal, then this electron is free. Now, what would happen? Another case is that suppose for some reason, so just now I said you that there are 10 to power 22, 5 into 10 power 22 atoms per centimeter cube that creates silicon crystal. So, there are 10 to power 22 atoms per centimeter cube, such a huge number. So, there is quite a good chance of non-zero probability that at some places, some atom might be missing. If that is the case, which is in left figure, if that is the case, then these 4 electrons of these 4 atoms are actually seeking for some other atom to bind with. So, these 4 electrons are actually not, so these 4 atoms are not in a stable structure. They are quite active, they are quite reactive, they are looking for partners, because they have only 7 electrons in their outermost orbit, which is not a stable structure, which is highly reactive state, highly reactive. So, what will happen in such case? in this case, only this place is reactive, because this is now these two atoms have only 7 electrons and they have not attained their stable structure, and it will affect the neighboring electronic configuration or energy configuration, and that will impact the outer circle of their electronic or energy configuration. So, ultimately the complete crystal is going to be affected by freeing one electron from one place, one site. In this case, it is more volatile because there are 4 atoms which are now highly reactive. Here there are only 2 atoms which are highly reactive. So, in such cases, how will we model such cases in our real life scenario when we want to make some device? Is something like this. Is something like this, that the bond structure which we saw in these 2 slides, which is based on the bonding of electrons or bonding of atoms. So, this bond structure can also be explained in terms of band structure, which we studied in the last class, how bands are created. An isolated atom, there are perfectly defined atomic level, sharp lines are there. As we go higher and higher in atomic number, these lines are closer and closer, come closer and closer, and at infinity this becomes continuum. But at n is equal to 1, n is equal to 2, n is equal to 3, for smaller n, so for the closure orbits closer to the nucleus, these levels are discrete and separated by a longer energy. But as we go higher and higher, so n is equal to 10, n is equal to 15, n is equal to 20, this separation becomes more closer, and after certain limit, you can model it almost as continuum. So, discreteness gets converted into continuum at higher orbit or higher principal quantum number states. At that level, you cannot differentiate between 2 electrons. They are at the same potential, equipotential field. But at lower stage, it is very difficult to escape an electron from n is equal to 1. It is easier to escape an electron from n is equal to 2. And we saw that if the situation changes from isolated atom to a system of many atoms, then those sharply defined energy levels are now split and they make a band, and that band creates conduction band and valence band separated by an energy gap that is called forbidden energy level. No electron or ion or atom is allowed to stay in that level. However, there is an energy, but electrons can't stay there. Electrons have to move from valence band to the conduction band. So, the bond structure or bond model of crystal can also be explained in terms of valence band and conduction band. In such perfectly fine crystal structure, this is the case which we have been discussing or knowing since last 2 classes, that the valence band is completely filled and the conduction band is completely empty. No free electron is there available in this crystal. So, the conduction band is completely empty. All atoms have occupied the most stable structure energy configuration. Therefore, the valence band is completely filled, and this crystal cannot conduct. It is perfect insulator at absolute 0 temperature, and this is this situation in terms of band model of crystal, band model of crystal. But in this case, where we saw that some by some means, by adding some energy, by heating the crystal, if you are able to let one electron free, then there is one excitement that you have created that makes these two atoms highly reactive, perturbed. This is explained in this band model, as if one electron from the valence band is liberated and it has come to the conduction band. This dark circle is that free electron, which has now reached to conduction band, and since there is only a single atom and the complete conduction band is empty, so it can go and sit anywhere. Like the classroom example I have been giving to you in last two classes, that if a first student who has come to the class and there are 300 empty chairs, he can sit anywhere. The second student who would come next to him has only 299 empty seats. One option is gone. So similarly, for this electron, moving in the conduction band is very, very easy, and so it will start moving in some particular direction just by flick of perturbation, and that movement in one direction is actually nothing but conduction or current. So the same material which was perfect insulator in this stage or in this configuration has now become a conductor. If some other bonding will break, then one more electron will come here. Other bonding will break, one more electron will come here. How to make more and more bonds? By adding more and more energy. If you keep on heating the crystal, many and many electrons are actually now occupying conduction band, and you will get more and more current. Magnitude of current will increase. In first case, it is only E by T. In second case, when there are 2 electrons, there is 2 E by T. 10 electrons, 10 E by T, where E is the electronic charge. So the magnitude of current is increasing by adding more and more, or by letting more and more electrons to come to the conduction band. And so as we go on heating or adding energy to the crystal, the conductivity increases. रूम टेम्परेचर पे जो कंडक्टिविटी होगी उससे ज्यादा टेम्परेचर कर दो, 40 डिग्री सेल्सियस कर दो और ज्यादा कंडक्टिविटी होगी, 45 कर दो और ज्यादा कंडक्टिविटी होगी, till the time it reaches to saturation. What is that saturation? Saturation is कि अब कंडक्शन बैंड में ही इतने इलेक्ट्रॉन हो गए कि there are no vacancy, there is no vacancy now, or there is a traffic jam. There are so many electrons that movement is not that easier as it was earlier. So electrons move तो करेंगे, but now with a steady state, with a steady velocity. वो फिक्स हो जाएगी velocity, जो terminal velocity है. तो ऐसा नहीं है कि आप कंडक्शन बैंड में इलेक्ट्रॉन ऐड करते जाइए और उसका कंडक्टिविटी बढ़ती जाएगी, ऐसा नहीं है. After certain time it reaches to its saturation. So from a semiconductor material there is saturation current for each different type of material. Now there is this situation, come to this is again a very interesting situation, that once we broke this bond, what will happen? These two atoms become very, very reactive, looking for another electron. That looking for another electron is possible by virtue of the 4 neighboring atoms. They may tend to break another atoms. They may tend to take away electron from another bond. How it is possible? Look here. So this atom is sort of one electron, is looking for 8th electron. This atom is also looking for 8th electron. ओके, तो अगर इनके पास एक इलेक्ट्रॉन आ जाए जो ये दोनों आपस में शेयर कर लें, दे आर हैप्पी। तो अब ये एटम क्या करता है कि ये अपने इस नेबर का ये जो शेयर कर रहा है, for some strange reason, all these studies at atomic level are probabilistic studies. आप पैटर्न कोई नहीं निकाल सकते। Everything you can study in probability terms. That probability of breaking this bond is this. That all you can say. So what may happen is that this bond will break, and so a single line is 1 electron that I told you. So this electron which is shared between these two atoms, now that will jump to this side, and now this electron is shared between these two atoms. These electrons are indistinguishable, so आप ये नहीं कह सकते कि नहीं भाई ये कैसे यहाँ आ सकता है। So now here there is a vacancy. ऐसा नहीं है, अभी कोई नया इलेक्ट्रॉन लिबरेट नहीं हुआ, सिंगल इलेक्ट्रॉन वाज लिबरेटेड which was made to move within the crystal in this form, बट यहाँ अभी लिबरेट नहीं हो रहा, यहाँ वो इलेक्ट्रॉन शिफ्ट करके इधर आ गया। So what is actually happening? Actually what is happening is that the electron, absence of electron which was here earlier, that has moved to absence of electron here. That may move to absence of electron here. That may move absence of electron here. So absence of electron is moving from one, shifting from one place to another place, just because the perturbation of these core atoms, just because perturbation that we have created by adding external energy, by breaking one single bond. I told you that absence of electron is known as, or is given name of another carrier, and that is hole. So in other words, what I am saying is that holes are moving, and holes are moving where? In the valence band. This is this fixed structure. This form structure is your valence band, completely filled state. Within this fixed structure domain or area or space or volume, absence of electron is moving now. So within this framework, holes are moving. So holes are moving in valence band, which is shown here. That hole is shown as just a circle, blank circle, not shaded circle. So if an electron is moving on right direction, holes are shown to be moving in the left direction. Why? Because if an electron sitting here is jumping to fill up this gap or this absence of electron here, then actually the hole which was here earlier has now moved to this place. So electron is moving from left to right, hole is moving therefore from right to left. And another property is also there, that if electron has negative charge, it is assumed that hole should have positive charge. तभी तो इलेक्ट्रॉन होल को फिलअप करने के लिए जाएगा ना. Negative will be attracted by positive, so electron will move to the location or site of a hole. अगर वो पॉजिटिव होगा तभी, अगर निगेटिव होगा वो भी, तो दोनों रिपेल करेंगे, तब कभी नहीं वो फिलअप करेगा. So hole has positive charge. Hole always moves in the opposite direction of the electrons. So there are two properties of hole that we have deducted just now by logic. Third property is that these holes have some mass. Obviously, अगर ये hole are opposite to electrons, electrons do have mass, so these holes also should have mass. अब ये mass क्या होगा? Question is whether this mass, mass of hole and mass of electron, are these same or different? That is the question. Is the question. Who would like to take this question? Give me 1 minute, I will just join you.
Sir, can you please repeat the question?
Yes, tell me. What should be the mass of hole? What should be mass of?
Sir,
Yes.
sir, we cannot say anything about exact mass, but we can say that charge to mass ratio of hole will be same as electron, but charge on hole will be negative of electron, that is positive.
And the ratio of charge to mass is same.
Yes, sir.
तो फिर तो इक्वल हो गया ना मास भी. E कह रहे हो कि सेम है, मैग्नीट्यूड ऑफ E, दैट रेशियो इज जस्ट इन टर्म्स ऑफ मैग्नीट्यूड, so E by m. रेशियो को
Yes, sir.
निगेटिव या पॉजिटिव से कोई लेना देना नहीं है. तो E by m कह रहे हो कि सेम होगा. E सेम है, the same 1.6 into 10 minus 19 coulomb, तो मास भी सेम हुआ, तभी तो रेशियो सेम.
Yes, sir. Mass भी same होना चाहिए.
Okay, Any other person? Any other person?
Hello, sir. Am I audible?
Yes, yes, yes.
Sir, we are modeling hole as an absence of electron. So, if an electron travels from A to B, we say that a hole has traveled from B to A. So, symmetrically, the mass of the hole should also be the same as the mass of electron.
Any other answer? नहीं? Okay, we will come back to this question later. यहाँ पे एक और concept में introduce कर रहा हूँ. So when we model in such crystal structure, when we model or try to model one atom in hydrogen-like atom, so the purpose of that modeling is to understand how much energy do we require to move one electron from valence band to conduction band. So that is all what we require. That is all what we require for that material to conduct. And I just said you that that is the only purpose of studying electrical property of a material, at how conductivity varies or how we can increase conductivity or how we can make material. अगर insulator की तरह use करना है तो how we can make insulator, how we can increase energy gap so that the material will become insulator, how we can decrease energy gap so that it will conduct easily. So all these type of things, all plays are actually focused towards how much is the EG. कितना आसान या कितना मुश्किल है बैलेंस बैंड के इलेक्ट्रॉन को मूव कराना, जंप कराना, रिप्लेस करना, प्लेस करना, नॉट रिप्लेस करना, प्लेस करना इन द कंडक्शन बैंड. एंड दैट डिपेंड्स अपॉन व्हाट इज द हाइट ऑफ ईजी. हाइट इसलिए कह रहा हूं कि एनर्जी हमेशा y एक्सिस पे हम ड्रॉ करते हैं, वर्टिकल एक्सिस पे ड्रॉ करते हैं. देयरफॉर हाउ high is my EG? That is the question. And can we manipulate, engineer, change that EG in any way? If we can, how? What is the mean of changing that EG? To understand that, we should start with this hydrogen-like atom. And in the hydrogen-like atom, in the last class, I showed you some slides जिसमें मैंने बताया था कि these are very basic calculation of calculating energy difference between two principal quantum number orbital orbits n equal to 2 से n equal to 1 के बीच में क्या energy difference है वो calculate करना was quite easy, and that you have already studied in either 11th or 12th standard. इसके basis पे Balmer line and Paston line and all those lines, radiation lines are defined. So in case of hydrogen atom, from n equal to 1 to n equal to 2, if I want to move the electron, the energy is, or the binding energy of the electron, single electron with its nucleus is minus 13.6 इलेक्ट्रॉन वोल्ट, जो हमने कल आपको जो भी क्लास था ट्यूसडे, तो ट्यूसडे क्लास में आई हैव शोन यू. Minus 13.6 or 13.6 electron volt is quite a high energy for breaking away the electron from n equal to 1 and letting it free to n equal to 2 or any higher state. Very large quantity. तो अगर in case of what this energy is in case of silicon, question number 1, तो सिलिकॉन के केस में क्या है कि +4 का कोर एटम है और -4 के वैलेंस इलेक्ट्रॉन्स है। -4 वाले वैलेंस इलेक्ट्रॉन को हमको हायर एनर्जी लेवल में ले जाना है, तभी दैट इज ब्रेकिंग फ्रॉम वैलेंस बैंड एंड गोइंग टू कंडक्शन बैंड। So there should be one energy for that. But on top of that, we have to think of कि can we decrease that energy? हम क्या ऐसा कर सकते हैं? Can we create some energy level in a pure crystal? Now this term comes, pure crystal, meaning there could be impure crystal. How do we create impure crystal? Or how do we add impurity in a pure crystal? वो impurity क्या करता है? Certainly impurity in a pure silicon crystal could be adding, let us say, one trivalent atom or one pentavalent atom or both. क्योंकि अगर मैं फिर से ग्रुप 4 के ही एलिमेंट को ऐड करूंगा, एटम को ऐड करूंगा, तो वो प्योर का प्योर ही रहेगा, उसमें कोई डिफरेंस नहीं आने वाला। हो सकता है सिलिकॉन एटम के क्रिस्टल में अगर मैं गैलियम कहता हूँ, जर्मेनियम ऐड कर देता हूँ, ग्रुप 4 का जर्मेनियम भी है, ग्रुप 4 का सिलिकॉन भी है। बट इफ आई ऐड एट सम साइट जहाँ पे सिलिकॉन इज मिसिंग, इफ आई ऐड जर्मेनियम देयर, एट द मोस्ट इट विल इम्पैक्ट इट्स ए, जो 5.43 एंगस्ट्रॉम हमने आपको लिखा था, द मोस्ट इट विल इम्पैक्ट द लेंथ ऑफ दैट यूनिट सेल। क्योंकि अब बड़े साइज का एक एटम मैंने वहां लगा दिया है, तो बड़े साइज के कारण थोड़ा सा वो स्ट्रेच हो जाएगा, एक्सपैंड कर जाएगा। तो इंस्टेड ऑफ 5.43 एंगस्ट्रॉम इट माइट बिकम 5.45 एंगस्ट्रॉम, इट माइट, आई एम नॉट श्योर, बट क्रिस्टल प्योर का प्योर ही रहेगा। इम्प्योर करने के लिए मुझको या तो ग्रुप 3 एलिमेंट ऐड करना है या ग्रुप 5 एलिमेंट ऐड करना है। हो सकता है मैं गैलियम ऐड कर दूं या आर्सेनिक ऐड कर दूं। अगर गैलियम ऐड करता हूं तो वो एटम हाईली रिएक्टिव हो जाएगा, क्योंकि मैं एक सिलिकॉन निकाल के वहां एक गैलियम लगा रहा हूं। सिलिकॉन के पास 4 आउटर मोस्ट इलेक्ट्रॉन थे, वैलेंस इलेक्ट्रॉन थे, गैलियम के पास 3 ही है। सो सर्टेनली देयर इज वन गैप देयर। So one gap means absence of electron there. Absence of electron means there is one hole there. If I add our trivalent atom in place of group 4 atom in the crystal of group 4, in the pure crystal of group 4, if I add a trivalent atom, actually in terms of carriers, what I am doing is that I am adding hole in that. If I am adding hole in that, it means I am adding positive charge. Hole has positive charge. And therefore, that type of impure crystal is known as p-type crystal. P-type, positive type. Instead of a trivalent atom or group 3 element, if I add a pentavalent atom और ग्रुप 5 एलिमेंट, तो आर्सेनिक या फास्फोरस अगर मैं ऐड करता हूं, तो इनके पास क्या है, इनका वैलेंसी है 5, आउटर मोस्ट ऑर्बिट में 5 इलेक्ट्रॉन है। बट मैंने निकाला सिलिकॉन जिसके पास 4 इलेक्ट्रॉन थे, तो 4 इलेक्ट्रॉन तो नेबरिंग 4 सिलिकॉन एटम के साथ कंबाइन करके ऑल सिलिकॉन एटम, नेबरिंग सिलिकॉन एटम्स विल अगेन अटेन देयर स्टेबल स्ट्रक्चर। बट आर्सेनिक का जो 5th इलेक्ट्रॉन है वो तो हैंगिंग रह जाएगा, उसको कोई बॉन्डिंग उसकी नहीं होगी। इट इज अ सोल इलेक्ट्रॉन। अगेन दैट pentavalent element atom or that arsenic or phosphorus atom will remain very, very volatile. And that volatility of that atom or that crystal comes from one excess electron in the crystal. Now we have created one excess electron in the crystal. However, neighboring के सारे silicon atom अपना अपना they are now perfectly fine. They are happy that we got what we lost. But arsenic का काम नहीं हुआ, इसलिए वो हमेशा perturbed रहेगा. So electronic or energy configuration of that impure crystal now changed because of one extra negative charge. Since there is one extra negative charge in form of the fifth valence electron of arsenic, therefore such type of impure crystals or elements or material are called N-type material, negative type material, N-type. So by virtue of adding impurity in a pure crystal, we have created two types of elements. One is P-type material, another is N-type material. P-type materials are created by adding trivalent atoms and N-type materials are created by adding pentavalent material. ये तो हमने देख लिया. But अब ये N-type या P-type बनाने से फायदा क्या हो? Are we adding more headache? Because purity is purity. Purity is always sublime. Purity is always admired. So why do we require to create an impure material? So note that the fundamental or the unique or underlined or highlighted sentence that I have told you that in each case or in both of the cases, what we have done is that we have changed the energy configuration of the material. We have made at least one side of that crystal highly perturbed. That perturbation may be a boon in disguise, may be putting us in an advantageous position. How that advantage is in our favor, that we have to see. It might happen, or actually it happens, that in such cases when we add some impurity in a pure crystal, इसका दूसरा नाम आपको टेक्स्ट बुक्स में मिलेगा डोपिंग, डोप कर रहे हैं, DOPE. So when we dope our pure crystal by such impurities, we are changing the energy configuration, and that change of energy configuration is basically, अगर हम इलेक्ट्रॉन और होल के टर्म्स में देखें, which are मतलब फ्री इलेक्ट्रॉन और होल के टर्म्स में देखें, तो which are nothing but, अगर फ्री इलेक्ट्रॉन है तो वो कंडक्शन बैंड की चीज है, अगर वो होल है तो वो वैलेंस बैंड की चीज है. Actually what we are seeing is that this hole is sitting just above the valence band, and that electron is sitting just below the conduction band. So instead of adding minus 13.6 electron volt or minus 5 electron volt in the crystal to make a pure crystal's electron jump from valence band to conduction band, what we actually now require is to add that delta E, which is very, very less than Eg of the pure crystal. तो वैलेंस कंडक्शन बैंड के जस्ट नीचे जो एक इलेक्ट्रॉन, एक्स्ट्रा इलेक्ट्रॉन बैठा हुआ है, तो इंस्टीड ऑफ एडिंग 5 इलेक्ट्रॉन वोल्ट, 10 इलेक्ट्रॉन वोल्ट और 13.6 इलेक्ट्रॉन वोल्ट, it is possible that all these possibility or calculation actually are can be calculated very exactly. Instead of 13.6 or 5 or 6 or 7 or 10 electron volt energy gap एनर्जी गैप के इक्विवेलेंट एनर्जी के बदले might be possible that gap is delta E gap is just 0.1 electron volt, 0.2 electron volt, 0.01 electron volt. तो केवल मैं 0.01 इलेक्ट्रॉन वोल्ट एनर्जी ऐड करूंगा और पेंटावेलेंट एटम के ऐड करने से जो एक्सेस इलेक्ट्रॉन has been found in the pure crystal, now that excess electron is liberated, is free, is made free, because that is desperate to be free, to get free. नेबरिंग 4 सिलिकॉन एटम भी उसको चाह रहे हैं कि ये यहां से चला जाए, तो वी आर हैप्पी बिकॉज दे डोंट नीड दैट. और वो जो आर्सेनिक एटम है वो भी अब कह रहा है कि मेरी तो सारे ब्लॉक्स फुल हो गए हैं, सो व्हाट आई विल डू विथ माय दिस बेबी, लेट समबडी एल्स अडॉप्ट इट. All 4-5 atoms will look for somebody, some situation, some opportunity to leave that electron, and that opportunity comes from addition of that external energy that is very, very small in comparison to Eg, and hence doping in a crystal helps you make that crystal conduct. वो इलेक्ट्रॉन लिबरेट होके फ्री होके अब चला जाएगा इमीडिएटली इन द कंडक्शन बैंड, और वो होल जो वैलेंस बैंड के जस्ट ऊपर बैठा हुआ था वो जंप करके नीचे, इलेक्ट्रॉन का मूवमेंट ऊपर इज इक्विवेलेंट टू होल का मूवमेंट नीचे, आर द सेम प्रोसेसेस. तो होल जो जस्ट अबव वैलेंस बैंड बैठा हुआ था, इन केस ऑफ adding or doping by adding a trivalent atom, वो होल नीचे आ जाएगा वैलेंस बैंड में, अपनी जगह पे आ जाएगा. और वैलेंस बैंड में we have just seen that holes also can move. Movement of hole is actually equivalent to movement of a free electron in the opposite direction. If an electron is moving in some particular direction, current is flowing in the opposite direction. So the flow of current direction of the current is same as the flow of direction of hole. So agar valence band में we have made the hole to move, we are actually creating current, we are actually conducting through that material, and therefore doping a crystal makes the material, pure material, conduct easily. ये यहाँ पे कैलकुलेट करके दिखाया हुआ है कि इंस्टेड ऑफ -13.6 इलेक्ट्रॉन वोल्ट वी रिक्वायर ओनली 0.1 इलेक्ट्रॉन वोल्ट टू मेक द इलेक्ट्रॉन फ्री, अगर वो पेंटावेलेंट हमने ऐड किया है, या मेक द होल फॉल डाउन टू वैलेंस बैंड अगर हमने ट्राइवेलेंट एटम ऐड किया है इन द प्योर क्रिस्टल. Now coming to the question that I asked you 5 minutes or 10 minutes, कितना टाइम हो गया? It is already 15 minutes over, above. Sorry, anybody? Hello?
Yes, sir.
क्लास का टाइम 11:30. It is still 11:30.
Yeah, it is.
Yes, 11:30.
And it is now around. So ठीक है, तो we will start from here in the next class. Sorry, I did not note that it is already 15 beyond my class time. Okay, so I am stopping record. Stop recording. Stop sharing. ऑलरेडी सारे जाने लगे, ठीक है, Okay, so we will meet on Tuesday. I am closing